Hello everybody, this video is an introduction to binary. So you may have heard binary before, and you may have heard that it's how computers can communicate. You may have heard that it's ones and zeros and nothing else, and both of those statements are true. So I'm going to draw an example here. This is an example of a binary number, and this binary number here actually represents the number 5. So this is another example of a binary number, and binary numbers are used to represent real numbers, such as in this example 101 represents 5. This number here represents a number much greater than 5, and with binary we can also represent things like, emojis, we can represent letters, we can represent multiple different things, and these ones and zeros get transported from one machine to another. So it might get transported from your laptop to your friend's laptop, and you don't see all these ones and zeros being passed. What you might see is a message, and the message might say, hello, whoever. So I want you to keep in mind that this video is an introduction. I'm not expecting you to be able to know binary or be able to learn binary all within this video. This is just a really high level overview just to get you familiar with some of the names, some of the concepts, and in future videos we'll be going into detail on every single part that we cover in this video. So the next thing I want to talk about is a bit and a byte. So a bit is part of a byte, and a bit is actually just one of these ones or zeros. So a bit can be 0 or it can be 1, right? That's the only two options a bit can be, and it's only one of these. So then when we move on to bytes, bytes is a little bit different. So bytes is the same as a bit in the fact that it can only take in ones and zeros, or it can only contain ones and zeros. But instead of just having one value like a bit can have multiple values. So it could have like 1 0 0 1 1 1 0 1. So as you can see, if we count these up, we have 1 2 3 4 5 6 7 8. So we have 8 of these ones and zeros, and this is called a byte. So we could think of it as a byte is the same thing as saying 8 bits. So a byte, so 1 byte is the same as 1 bit multiplied by 8, or 8 different bits. And we use the words both bit and byte, but more so byte, because if we want to represent a number like this number 5 here, we would represent it using 8 bits. So it's the same if we want to go and represent like a letter A or B or C, we'd represent it in a byte, because we can't use a bit because a bit would be too small. So you can see, for example, the number 5 here contains 3 bits. So we'd never be able to represent 5 using just 1 bit. So we can use bytes because we have more flexibility. We have 8 possible different combinations. We have 8 different slots to use either 1 or 0 in. So you might have heard of binary being called base 2. And the reason why it's called base 2 is because there's 2 different outcomes, right? As we discussed before, it can be either 0 or 1. That's what binary is. It's 1 or 0. Then we also have base 10, which you're probably more familiar with. So base 10 is what we'd use in the likes of normal maths. So in base 10 we can use numbers like 0 and 1, so it's the same as binary, but in base 10 we can also use 2 and 3 and 4 and 5 all the way up to number 9. So 0 to 9 gives us 10 different possibilities, while base 2 gives us 2 different possibilities. Base 10 is a much better way of representing numbers because you can represent different numbers and different quantities using a smaller amount of space. The problem is with computers, they can only understand ones and zeros, and the reason behind this is because it's an electrical device. Okay, so it's plugged into your electricity supply, and the computer is supplied with current. So when we think about current coming in to supply our machine with power, so when we plug in our computer, or if we have a battery in our laptop, we're supplying power to our machine. So then we can create a voltage, and the voltage can be one of two possibilities. The voltage can be low or the voltage can be high. If the voltage is low, we represent this in the computer as a 0, and if it's high, we represent it as a 1. That's the issue. It's fundamentally the way that computers work. You could argue that could we not have like a medium, and then you would have like a voltage which would be in between 0 and 1. They've tried this in the early days of computing, but there was problems. What would happen is sometimes if you have let's say a medium value in here, the medium value could sometimes be, misread by the computer, and the computer may think that the medium value is actually a low value because it's quite close to 0, or it might think it's a high value because it's quite close to the higher value threshold. So that's why they decided in the end to go with just 0 and 1, so high and low. So the final thing that I want to discuss in this introduction is gates or switches. So if we have a computer, and you can imagine that it has a certain state, let's say we're storing a value like before. Let's say it's 101, which we seen in the beginning of this video represents the number 5, okay? But then maybe we want to change this number. We want to change this number to maybe add 1, so we want to add 6, or maybe we want to take 1 away from it, so we want this number to represent 4. Now to do this, we have to use like switches and gates. And what happens with these gates, sometimes referred to as logic gates, these logic gates will take in binary, they'll take in our ones and zeros, and they'll perform some sort of manipulation on them. So for example, we have 3 main types of gates. We have an AND gate, we have a NOT gate, and we have an OR gate. And what these 3 types of gates do is they take in values and then they provide us with an output. So for example, with the AND gate will take in 2 values. It could be 0 or it could be 1. And if these numbers are both correct, we will get an output which will be either 0 or 1. In this case, these two would have to be the same, so they're not the same, so we'd get 0. A NOT gate takes in 1 value, so it could be 1 or it could be 0. So if it takes in 1 or 0, the output will be whatever the opposite of that is, so it could be 1 or 0. Then with OR, we can take in again, we take in 2 values, which is 1 and 0 in this case, let's say. So if either of these values are true or 1, our output will be 1. So we'll see this. I'll go into this in more detail. I'll be going through examples of the different types of gates again. I'll be going through a detailed description of how they work, along with multiple examples. But this is just a quick introduction to binary and how computers work. Hello everyone, in this video we're going to learn how to read binary. So while reading binary we can compare base 10 to base 2. So base 2 is our binary way of counting and dealing with numbers, while base 10 is the one that we're more familiar with, the ones that we would have used in maths before. So we use the numbers from 0 to 9, while in binary we only use the numbers from 0 to 1, or 0 and 1. So if we look at these two numbers here, using the normal way of counting, we can see that this number here is 754, and we can see that this number is 104. Now, we all know this, but one thing that we might have forgotten about is when we look at this value here, or this column, so we can imagine this as being a column. So in this example here, we can see that they're both 4. So while we were in primary school, we probably referred to these different columns with different names. So usually when we looked at this first column here with the 2 4s in it, we would have called these units. And then we understand when we reach 9 here and we want to add more to it, we have to change this and we carry on 1 to our tenths. And we call this next column here tenths. And then the same happens when we have an extra field or an extra number here that we can't fit it in. So for example, if we wanted to add the number 6 to 5, we wouldn't be able to put in 11 here. So what we do is we would leave 1 and then we would carry 1 onto this next column here, which is the hundredths, and then we would increase this number here from 7 to 8. Now I think we all get this idea, but another thing we can do is, rather than using these names called units and tenths and hundredths, we can think of each of these columns as having a power. So since this is base 10, we can say that this first column here is the same as saying 10 to the power of some number. And where do we start counting? We start counting at 0. So 10 to the power of 0, we can say is this column. We can say 10 to the power of 1 is the next column here. And then we can say, for the final column in this example, we have 10 to the power of 2. So if we do some quick calculations here, we can see that 10 to the power of 0 is equal to 1. Now keep in mind here that if we have any number to the power of 0, it's going to be 1. So for example, in this case, 10 to the power of 0 is 1, but it's also true that 8 to the power of 0 is 1, and that 5 to the power of 0 is 1. And when we go and look over at this example, 2 to the power of 0 is also 1. So just keep that in mind. Any number to the power of 0 is always equal to 1. Now we start to change a little bit when we get to 10 to the power of 1. So 10 to the power of 1 is the same as saying 10. So if this was 5 to the power of 1, it would be 5. If it was 2, it would be 2. Now we step it up again and we go 10 to the power of 2. So in this example, 10 to the power of 2 is equal to 100. And this is a really long way of understanding what this number is. So we all know that this is 754 and we all know that this is 104. But this example will help you because we're going to be taking the same approach when we start to learn about binary and base 2. So if we go and look at our first number here, we can see that it's 4. So we can see that this is 10 to the power of 0, which is 1. And then if we multiply this by the number here, so multiply this by 4. And then we come over here and we see 10 to the power of 1. So 10 to the power of 1 is 10. Okay, so then the number under here is 5. So we can multiply this by 5. And then if we move on to the next column, we can see 10 to the power of 2 is 100. And our number here that we're dealing with is 7. So we need to multiply by 7. So if we multiply all these numbers here, our answer we'll get is 1 multiplied by 4 is 4. 10 multiplied by 5 is 50. And 100 multiplied by 7 is 700. So if we add all these up together, the number that we're going to get is 754. This is just another way of representing it, but it's a good way to be able to understand how exactly we come to these conclusions, and it'll be really useful when we start working with binary. So this is a binary number here, okay? Now for this example, we're going to deal with a slightly smaller binary number, just for simplicity, but we will come back to this number. So if we take the number 1, 0, 1, okay, so you may have remembered from the last video that we used this number before, 1, 0, 1. This is actually equal to 5, but by looking at it, you can't really understand how it's equal to 5. So if you remember, in our base 10 system, we started off here going 10 to the power of 0, 10 to the power of 1, 10 to the power of 2. So we're going to do a similar approach with this example, but it's not going to be 10 because we're not dealing with base 10. We're dealing with base 2 this time. So we'll get a 2 and we'll put it to the power of 0. We'll get a 2 here and we'll put it to the power of 1. And we'll have our 2 to the power of 2. So if we go and multiply these out, if we remember 2 to the power of 0 is equal to 1, because remember, anything to the power of 0 is equal to 1. Then we move on to 2 to the power of 1. 2 to the power of 1 is equal to 2. And then if we discuss 2 to the power of 2, this is equivalent to 4. So we've got our values here. Now we need to multiply them by something. So in our previous example, we multiplied them by whatever number was underneath them. So for example, if we had a number 5 here, we would multiply 1 by 5. So we'll do the exact same thing in this example. The only thing that looks a little bit strange is we're just dealing with ones or zeros. 2 to the power of 0 multiplied by 1b. So we've got 1 here, so it's going to be 1 multiplied by 1. And then this next example, it's going to be 1 to the power of 2, which is 2. So it's going to be 2 multiplied by 0. And then in our next example, it's going to be 2 to the power of 2, which is 4. So it's going to be 4 multiplied by 1. So we put 1 in here. So if we multiply 1 by 1, we can see this is going to be 1. If we multiply 0 by 2, we can see this is going to be 0. And then if we multiply 4 by 1, we can see that this will be 4. So if we go and add all these together, 4 plus 0 plus 1 is equivalent to 5. So this is how we're able to understand binary, and we can see that this number 101 is actually equal to 5. Hello everyone, in this video we're going to be converting from binary to decimal. So to start off with, we need a binary number, so we're just going to create a binary number. It doesn't actually matter what it is, but for this example we'll just make up a binary number. So we'll say 1 0 0 1 1 0 1 0. So in this number we have 8 digits. So in this example we have 8 digits, or we can call them 8 bits. And what we want to do with these 8 bits is we want to find out what number this actually is in the base 10 system that we're normally dealing with. So if you remember from our last video, when we worked with binary, we needed to look at the power of 2. So for each of these digits here, they're associated with a power of 2. So for example, this one here would be 2 to the power of 0. This would be 2 to the power of 1, and so on and so on. So I'm just going to fill these in. 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and 2 to the power of 7. So we're going to do some calculations now. You can use your calculator if you want, but after you've done this a few times, you can actually memorize all the different numbers. So you'll know that 2 times 2 to the power of 0 is 1, and you'll know that 2 to the power of 1 is 2, and so on, so on. So this next one here will be 4. You can check this on your calculator if you wish, and you'll see we get up to quite a big number pretty fast. So we have 32, we have 64, and we have 128. So we need to go and start to look at our binary number here. So we can start off by looking at it on the left hand side. So we can see that 128 here, which is 2 to the power of 7, has got a 1. So if it's got a 1, it means that this placeholder is being used. So another way of thinking about this is we can say 128 plus whatever else we've got here, or whatever else is 1. So when we go to our next step here, and this is 2 to the power of 6, and 2 to the power of 6 is equal to 64, but this isn't 1, this is 0. So if we were to multiply 64 by 0, it would be 0. So we can write down 0 here if we want, or if you want, you can just ignore it. This 128 here had a 1, so we couldn't ignore it. That's why we wrote down 128. But we'll write down the 0 here just to make it a little bit more clear. So next we're going to have to add in this column. So it's quite similar to the 64 because it's got a 0. So we can just put down a 0 here. Again, as you move on to your second example or third example, you don't have to put in these zeros. You can just write down the number itself. So now we get to 16. We can see that 16 has got a 1, so we have to add 16 to this. And we put in a plus as well. And 8 has actually got a 1 as well, so we have to also add 8. And we'll do another plus. Now we can see that 4 has 0, so 4 times 0 is 0. So then we'll add in 2, so 2 times 1 is 2. And we can see for the last element that we've also got 0 as well, so we can just add in 0 or nothing. So now that we see this, we have to add up all these elements. So if you add up all these together, you'll find out that the total will be equal to 154. Now, another way you can actually do this is if you have, let's say, a number, for example. Let's imagine you had the number 154, right? So if we have the number 154 and we want to go and convert this into binary, so this time we're given a number and we want to convert into binary, what we could do is we could get our number that we're given, so 154. So keep in mind, this is a brand new example. Our aim over here was to convert from binary to decimal. So that's what we've done. So this is our binary number. We've added up our bits. We've calculated that the decimal form is 154. So we've done that. Now we're moving on to a new example. So given 154, we want to go and get this number. So this binary number, or this binary representation. So with our given number, we need to take away something from it. Okay, so the first thing we need to see is we will go to the far left and we'll see if it's possible for 128 to be taken from 54. So if we take 128 from 54, we can do this without getting a negative value. So we'll say 128. And we'll draw a little chart down here at the bottom so that we can keep track of what we're taking away. So we can start off with, let's say, our first one here, which would be 1, because we can take off 128. Then after we take 128 from 154, we are left with 26. So we've got 26, so we can put 26 down here. Now we want to take away a number from 26. So if we go here and we look at the next number which can be used, which is 64, we can't take 64 away from 26 because we're going to end up with a negative number and we don't want that. So we're going to add in a 0 here because we cannot use 64. Similar to 32, we're going to look at 32 and see can we take 32 away from 26 without leaving a negative number, and we cannot do this either, so we're going to put in another 0. Now we go and we look at 16, so we can actually take 16 from 26 and not be left with a negative number. So 16 minus 26 will leave us with 10. So we can actually add in a 1 here because we've taken 16 away. Now we've got 10 left again, we've got a number, it's not 0, so we need to take away. So when we go over here and we look at 8, we can see that we can take 8 from 10, so this is brilliant. So 8 minus 10 will leave us with 2, so then we can bring 2 over here. Now remember, since we've taken 8 away, we can add our 1 down here. Now we've got 2, and now we're looking to take something else away from 2. So if we move on to 4, which is the next smallest number, 2 is smaller than 4, so we cannot take 4 away, so we need to put a 0 here. Then if we go up here and we look, okay, this is 2, so we can actually take 2 from 2. It'll leave us with exactly 0, but that's okay once it's not a negative number. So we can take 2 from 2, we've got 0, and now we can add a 1 in here. And once we've got to 0, we can just fill the rest in with zeros because we know we've got to 0. But we'll just go through this step as we did with the other examples. So we are left here with 0. So if we want to try and take something away from 0, it's not going to work. So we can see if we try and take 1 from 0, it's going to leave us with a negative number. So there's no point in even doing this step, but we just skip that bit and we put in a 0 at the end. So remember, when you get to 0 here, you can fill the rest of the bits in with 0. And if you go and check this binary number here against the one up here that we started with, they're exactly the same. So you always want to check from this. So you always want to check for this. Hello everyone, in this video we're going to be counting in binary. So you can see on our board we have a list of numbers from 0 to 12 in our normal format that we're used to dealing with, which is decimal. So we're going to convert these numbers from 0 to 12 into their equivalent binary numbers, and to do so we're going to use our powers of 2 table to help us out. So to start off with our powers of 2 table, we're going to go 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. And we're only going up to 2 to the power of 3 this time because that's all we need for this video. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and 2 to the power of 3 is 8. And the reason why we're only going up to 2 to the power of 3 is because if we have a number like 1, 1, 1, 1, this is the highest number that we can represent just using our 4 digits, or 4 bytes we can call them. So this binary number here is actually equivalent to 15, and the reason why is because if we add 8, 4, 2 and 1 together, we'll get 15. So 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So this table can help us out as we're going through our binary numbers. I want to mention something quickly that we've went over in previous videos a little bit, and I just mentioned it there a second ago, is the fact of having a bit. So when we had our 4 ones here, I said that these were 4 digits. Or another name, we can refer to them as 4 bits. So a bit can be either a 0 or a 1. So you'll see as we're going through these numbers, for these numbers we might be converting it into a binary number. Now some of the binary numbers may require just 1 digit to represent it, like 0 or 1. Some other numbers might require 2 digits or 2 bits, like 2 and 3, and then some other ones will require 4 bits, like 12 and 11 and 10. So just keep that in mind. So as we all know in binary is 1 and 0. So we can represent both the numbers 0 and 1 in decimal and in binary. So when we're converting from decimal to binary, it's going to be the same. It's going to just be represented as a 0. And the same goes for 1. If we have 1 in decimal, it's also represented as 1 in binary. Now this is where things start to change a little bit. It's when we get to the value of 2 and 3 and 4 and so on. So when we get to the value of 2, normally we represent it like this, but in binary it's represented like this, 1, 0. And I'll tell you how we come about this. So if we have, let's say, 1 and we have another 1, and we want to add these together, right? So if we were to add these together, normally we would add 1 and 1, which would give us 2. But with binary we can't really do this. That's because we can't represent the number 2. So what we have to do is we have to bring our 1, we have to carry, and we can carry 2. So we've got 2 here, so we can carry our 2 to the next column, and this will be 1. And once we've carried it, we can then put down a 0 here. And then we bring down the 1, and it's represented like this. In the next coming videos, we'll be going into more addition and subtraction in binary, so if you don't quite get this yet, don't worry about it. Now, another way we can look at adding binary numbers or converting our decimal numbers to binary is by looking at our little table over here. So if we look at this, and we can see that this number is 2, this number is 1, this number is 4, and this number is 8. If we have our number 2 in decimal, how could we make up the number 2 just by using these numbers? Well, we could just use the number 2 here. So we could say that we want one of those 2's, and we don't want anything else, so we can just fill in all the other places with 0. And that's what we do here. Now, you could also put in 2 zeros here as well, indicating that you don't want 8 or you don't want 4. But for this example, we're just going to represent the numbers like this. So then when we move on to 3, let's say we have 1, 1, and 1, and we want to add these together. Now again, in decimal format, we can just add these 3 together and get the number 3. The problem with binary is we can't even represent 2. So if we can't represent 2 in binary, we definitely can't represent the number 3. So again, we're going to have to carry on to the next column. So what we can do is, we've got 3 here. So to create a next column, we need 2. So we can carry 1. So that's basically the same as saying we've got 3 here, we've taken 2 away, we've added to the next column. So if we've taken 2 away from 3, it's going to leave us with 1. So we can just put 1 down here, and then we're going to bring down this 1 also. So it's going to look like this. It's going to look like 1, 1. So we put this down here for 3. So if we want to go and figure this out using our table, we can think about what numbers here can we use to get 3. So we could use 1, 2 and 1, 1. So that would work. So 2 plus 1 is 3. So again, you see that we have 1, 1 here, which is the same answer we got doing it the other way. Now I'm going to let you run through the rest of them. I'm going to do them out for you so you can check your answers. So these are the rest of the answers, and if we want to go and pick one of these numbers just to double check it, so let's say for example we pick the number 9, and we want to make sure that this binary number is actually 9. So what we can do is we can go over here and we can write down the binary number that we think equals 9. So 1, 0, 0, 1. And what we can do is we can go and look at these numbers above, so we can say that, okay, this is the same as 8 multiplied by 1 plus, so there's no need to do 4 multiplied by 0 because that's just 0, 2 multiplied by 0, that's just 0, so there's no point in writing it down. And then we've got 1, so we can multiply 1 by 1, so 1 multiplied by 1. So 1 by 1 will be 1, then we're going to add 8 multiplied by 1, which is 8. And this gives us our answer as 9. So we can check our answers using this method. Now, one thing that I touched on earlier on in the video is this idea of our bits. So you can see now what I meant when I said 1 and 0 you are using 1 bit. And you can see the likes of 4 and 5 are using 3 bits, and 11 and 12 and 10 are using 4 bits. So this is not actually the way it's represented. So this isn't fully correct, because if we declare a variable and it only has maybe 2 bits in it, if we want to increase that number to a larger number that will need more than 2 bits, then we can't actually do it. So for example, if I create a variable, this syntax is going to be JavaScript. So let num equals 5. So that means that we can redefine the contents of this variable whenever we want. So num is the name of the variable and it's equivalent to 5. We've assigned 5 to this variable. So we can see from here, our table shows that 5 is equivalent to 1, 0, 1. So this is our binary number. Now, if we have a variable that just has 3 bits, because this is 3 bits, 1, 2, 3, and then we want to change our number from 5 to 10. So for example, let's say we're redefining our num. So we say num equals 10. Now the problem we have is we have a num that we've defined and it's able to hold 3 bits. But now we're trying to assign 10 to num. So if we look at 10 here, we can see that it has 4 bits. So there's just not enough space. So the way we get around this is by giving a variable loads of space when we initially define it. So while we've assigned this to 5 and 5 only needs 3 bits, we actually give the num variable 16 bits or 32 bits. So for this example, I'm going to use 16 bits. So some programming languages use 32 bits to hold their integers, some use 16 bits, and some give you an option of deciding on how many bits you want an integer to take up. For this example, I'm using 16 just because of space. So how this example would work is 101 is equivalent to 5. So on this line here, where we define our num as 5, we would have 1, 0, 1, and then all the rest of our numbers here would be 0. So it would look like this. Now, when we want to change from 5 to 10, we can just get rid of these 3 bits, and we need to change this 4th bit here, and we're going to change it to 1010 because 10 is equivalent to 1010 in binary. So we just put down 1010, and now we've changed our num variable from 5 to 10. And then we can also change this from 10 to maybe 105 or 1005 or 99 or whatever other number we want. Now you might be thinking, these bits here are all wasted. So, you know, if I'm only gonna count up to 15 or whatever, can I not just use 4 bits? Because if I know my number is never going to be greater than 15, can I not use 4 bits? You can in some programming languages, but you need to take into consideration in most cases you're not going to be sure what number the user is going to put in, or the maximum number that the user is going to put in. So you're going to want to have a margin of safety. So you're better off going with a much larger number and you're able to take in whatever the user puts in, rather than not being able to store whatever number the user gives you. So it's up to you as a programmer to decide what you want more. Hello everyone, in this video we're going to be adding binary. So we're going to start off with some super simple examples, so I'm going to jump right in. If we have 0 and we want to add another number to it, we're going to choose 0 for this example. We're going to get 0. Okay, and if we have 1 and we want to add 0 to 1, we're just going to have 1. I think this is pretty straightforward and everyone can understand this. Where it becomes a little bit more complex is when we go beyond 1. So for example, if we have 1 and we want to add another 1. So in traditional maths we would know that this is equivalent to 2, but in binary we can't do that because 2 doesn't actually exist as a number. So 2 in binary actually is represented by 1, 0. So how do we get there? So if we take an example in traditional maths, if we have a number like 5 and we want to add another 5 to it, so we all know if we want to add these two numbers together, it's equivalent to 10. But how do we exactly get to 10? We know when we put 5 and 5 together that we carry 1 to the next column. We can cross these out and we know we carry 1 to the next place. Then we just put down 1, then this column's total is 0, so we write down 10. So in a similar way, that's how our binary numbers work. So we've got 1 plus 1, which is 2. We can't represent 2, so we carry it to the next place. And the answer is represented as a 1, because this one here, we bring it down. And now these two 1s here have been moved forward to the next column, so these are also equal to 0. So 2 in binary is represented as 1, 0. Now, what if we want to add more than 2? What if we had like 3 or 5? How exactly does that work? So if we have 1, and we want to add another 1, and we want to add another 1, so this would be equivalent to 3 in decimal. So if we jump into a decimal example first, it might make a little bit more sense. So instead of having 5 and 5, let's say we have 5 and 5 and 5, and we want to add these three up together. Now, we all know that this equals 15, but what exactly is happening? So again, we know when we reach 10, we have to carry it on to the next column. Okay, so it's 10 in our decimal format that we're used to dealing with, while in binary it's 2. So that's where we get base 10 versus base 2. We know that 5 and 5 is 10, so we can cross them out and we can carry 1 to the next column. And then if we bring this 1 down and we see what's left here, 5's left. So similar to this example, we have 3 1s. So we know that we can't represent 2 in binary, so we definitely can't represent 3. So what we can do is we can get rid of these 2 1s and we can carry them, and we have this 1 left over here. So we're going to bring these 2 down. So we'll bring this 1 down and bring this 1 down. This 1 1 is the equivalent of 3 in binary. So let's jump into a better example. Let's assume we have the number 1 0 1 0, and we want to add the number 1 0 0 1. Now, if you remember from the previous video, you might remember that this 10 10 is equal to 10, and that this 1 0 0 1 is equal to 9. But if you know that or you don't know it, it doesn't matter. You should still be able to find the total of these 2 binary numbers without knowing their decimal form. We'll put down our first number, 1 0 1 0, the same way that we'd do in traditional maths, and we put whatever number we want to add to it underneath it. Again, this is something that we're very familiar with traditional maths. We're going to add these numbers together. So if we have 0 and 1, what's 0 and 1? It's 1. What's 1 and 0? Again, it's 1. 0 and 0 is 0, and 1 and 1, okay, so that's 2. So what we could do is we could look back up here what we done when our answer was 2. So we carried 1 to the next column and it was left with 0. So this number here is the exact same one that goes down here. So we're going to just jump into another example just to make sure that this is clear. So we're going to have our example as 1 0 0 1 1 0, and the number we want to add to it will be 1 1 0 1 0 1. So again, we're going to add these numbers together. 1 and 0 is 1, 0 and 1 1, 1 and 1. Okay, so that's 2. So we can't write down 2, so we need to carry it. So we're going to just put a little 1 here so we know we're carrying it, and we can just cross these out. We don't have to use them. So we put a 0 here. Now we look at this. So this is 0 plus 1. That leaves us with 1. Then here we have 1 plus 0. Again, this is 1. And 1 and 1. And we know 1 and 1 is equal to 2. And we know 2 in binary is equal to 1 0. So if we want to make sure that our answer is correct, we can double check it by creating a little 2 to the power of grid. So I'm going to go through that quickly. You would have seen this in previous videos. So if we count our 1s and 0s here, we can see there's 1, 2, 3, 4, 5, 6, 7. There's 7 1s and 0s. So we'll have to go up to 2 to the power of 6. That gives us 7 different places. So if we run through this, 2 to the power of 0, 1, 2, 4, 8, 16, 32, and 64. So what we can do now is we can write down our binary number that we have, which is 1 0 1 1 0 1 1. Now, to make sure that we're correct, it's always good to convert our binary numbers into decimal, and then we can add our decimal numbers to make sure that we're correct. So we're looking for the answer at the moment. So we can see if we get 64 and multiply it by 1, and then we get 16 multiplied by 1, 8 multiplied by 1, 2 multiplied by 1, and 1 multiplied by 1. That will give us our answer. So if you go and multiply these all out together, you get this, and then if you add all these numbers together, you get the answer as 91. So what we can do now is, we know that this binary number here is equal to 91. So the next thing we need to do is we need to get these other 2 binary numbers, and we need to convert them into decimal, and then we can add these 2 numbers together when we've got the decimal format, and we can check to make sure that it's 91. So now we've got our binary number here, and we can see that it's equal to 32 plus 16 plus 4 plus 1. If we add all these up together, we can see that it's equivalent to 53. So we can put 53 over here to make sure that we don't forget about it. So if we get the numbers 53 and we add 53 with our other number, which is 38, and we get our total will be 91. And this is one way we can make sure that our binary number that we've solved is actually correct. So this is the final example that we're going to go through. This one's going to be a little bit more difficult. So our number is going to be 1 0 1 1 0 1, and our number that we want to add to it will be 1 1 1 1 0 1. So the last time we added our binary numbers together, and then we converted them into decimal, and then we added the decimals to make sure that we were correct. We could also do it the other way around. So before we go and add these together and get a result, we could convert these two binary numbers here to decimal. We're going to do it this way this time. We bring these binary numbers over here into our little grid, so it's easier for us to figure out what the equivalent is in decimal. So for this first binary number here, you can see it's equal to 32 plus 8 plus 4 plus 1, which comes to a total of 45. Then we can do the exact same thing with this other binary number. Our second binary number is equivalent to 32 plus 16 plus 8 plus 4 plus 1, and this total is 61. So if we have 45 as our first binary number and 61 as our second binary number, we take our number 45 and 61, it gives us a total of 106. So what we can do now is we can get our 106 number and we can convert that into a binary number to find out what number we should see here. So what we can do is we can take our number, which is 106, we can take away the biggest number we've got, so that would be 64, so minus 64, and that leaves us with 42. So we can put a 1 here. Then we need to see, can we take our next biggest number from 42? So our next biggest number is 32, and we can take it from 42. So if we have 32 minus 42, will leave us with 10. So we'll also put a 1 here beside the 32. Our number is now 10, so we can't take 10 away from the next biggest number because our next biggest number is 16. So we have to put a 0 in there. Now we look at our next biggest number, which is 8. So we can take 8 away from 10, which will leave us with 2. So we can put a 1 in this 8's column. So we're left with 2. So can we take 4 away from 2? We can't, because it would leave us with a negative number. So we're going to put a 0 in there. We look to our next column, which is 2. So we can actually take 2 away from 2. It will leave us with 0, but we can do it. So we're going to put a 1 there. And once you've reached 0 here, you can fill in all the rest of the columns with 0, or you can do it out. So you could bring down 0 to the next line, and you could check to see, can you take it away from the next number, which is 1. Again, you can't take anything away from 0 without leaving you with a negative number. So we're just going to fill in 0 for this. So this number here, 11011010, should be our answer. So let's go and do it out. So 1 and 1 we know is 2. So we're going to put a 0 down here. We're going to carry our 1 along here. And we're going to put down 1 here, because 0 plus 1 is 1. Again, 1 and 1 is 2. We're going to put down a 0. We're going to carry this 1. Now we've got 1 plus 1 plus 1. This is now equal to 3. So we could get rid of 2 of those. We could carry it, so we carry it on to the next column. But we still have 1 here, so we need to put down our 1. Now we have 1 and 1. 1 and 1 is 2. Again, we're going to put down our 0. We're going to carry our 1. Now we've got 3 different 1s we have to add up. So we know 3 1s is equivalent to this. So 1, 1. So if we compare this 1, 1, 0, 1, 0, 1, 0 to this number here, they should be exactly the same. Hello everyone, in this video we're going to be subtracting in binary. So similar to our last video where we were performing addition on binary, we're going to jump into some really basic simple examples. So we'll start off with taking away 0 from 1. So if we take 0 from 1, it'll leave us with 1 because we're taking away nothing from it. If we have 1 and we want to take away another 1, then we're going to be left with 0. I think we all understand this. Now, where it gets a little bit more difficult is when we jump into numbers greater than 1. So when we jump into numbers like 2, 3, 4, and so on, so on. And the reason why it gets a little bit more difficult is because binary only holds 1s and 0s. So when we jump into 2, or numbers greater than 2, we have to represent it in a different format than what we're used to. So you should know by now that 1, 0 is equivalent to the number 2 in decimal, and the number 1 is just 1. So what we're going to do here is we're going to take our number 2 away from our number 1. And what we're going to do here is we can't take away 1 from 0 because it'll leave us with a negative number. So what we do is we borrow from the next column. So this next column now becomes 0, and this column here becomes 2. So we now can take 1 from 2, which will leave us with 1. And we can just bring our 0 down, or if we want, we could leave it blank. But in this scenario where we change it to 0, It's always good practice to bring the 0 down. Now this time let's jump into a slightly more complex problem. We're going to have 1, 0, 0. Now if you remember from our videos where we were counting in binary, you know that this number is equal to 4 in decimal. And the number that we're going to take away from it is going to be 1, 0. And you should know that 1, 0 is the same as 2. So if we want to take 2 from 4, it'll leave us with 2. We all know this, but we want to know how we go about doing it in binary. So 0 from 0, we don't have to take anything away, so we can just leave that as 0. Now we encounter a problem, again similar to last time. When we want to take 1 away from 0, we can't do it. So we borrow from the next column. The next column loses 1, so in this case becomes 0. Now we've got 2 over here. So now 2 minus 1 leave us with 1. And as you can see, this is equal to 2 in decimal. Again, we're going to go through another example. This one's slightly more difficult, but not too difficult. So 1, 0, 0, and we're going to take away 1, 1. Now, as you can remember, 1, 0, 0 from our last example we know is 4, and 1, 1 you might remember from some of the previous videos is 3. So we should be left with the answer as 1 here. So again, we want to take 1 from 0, but we can't do it because we can't take 1 from 0 without leaving us with a negative number. So we want to borrow from the next column. But again, we have a problem here. We can't borrow from the next column because it's also 0. So we need to borrow from the next column. So this 1 will become a 0. This column here will become a 2. And now this column here wants to borrow from this column since it's no longer 0. So this will be changed from a 2 to a 1, and this column will now be a 2. So we can now take 1 from 2, which will leave us with 1. We can now take 1 from 1, which will leave us with 0, and we can just bring down our 0. And as you can see, this number here is equal to 1. Stepping it up another little notch, we're going to have our binary number as 1, 0, 0, 0. Now you'll probably remember, again from our previous videos, this number is equal to 8. And we're going to take away from 1, 1, 1. And this number is equal to 7. So similar to last time, we want to take 1 away from 0. We can't do this, so we need to go to the next column. Again, this is also 0. We have to jump to the next column. Now we need to jump to the next column, which is actually a 1 that we can borrow from. So this 1 will become a 0. This column here will become a 2, but we have to take 1 from it for the next column, so it becomes a 1, and now this column becomes a 2. But we also have another problem. This column is 0 and it needs to borrow. So this column is changed to a 1 also. Now this column is left as 2, so now we can take 1 from 2, which leaves us with 1. 1 from 1 leaves us with 0. 1 from 1 leaves us with 0. And we can bring down our 0 if we wish. Again, this binary number is the same as 1, so it's the same as the previous example. One more medium question before we go into the harder binary questions. So we're going to start off with 1, 0, 0, 0, and we want to just take away 1. That's all, just want to take away 1. So similar to last time, we want to take away 1 from 0. Again, we can't do this, so we need to borrow. Again, we can't borrow from this one, so we have to jump another column, and also here we have to jump another column. So this becomes 0, this becomes 2, we're going to borrow, so now it's 1. This becomes 2, again, we're going to need to borrow, so it's going to become 1, and this is left as 2. So now when we take 1 from 2, leaves us with 1, we can bring down our 1, we can bring down our 1, and we can bring down our 0. So we're left with this number. So now the question is, what is this number here? So it's the same as last time. This number is 8, this number is 1, and if we want to take 8 away from 1, it leaves us with 7. And this number here is equal to 7 in binary. So the next two questions we're going to go through is going to be a little bit more difficult. So we might need our 2 to the power of grid to help us out. You'd have seen this in previous videos, so I'm going to do this really quick. Okay, so now we've got our grid completed. You can see that we went from 2 to the power of 0 to 2 to the power of 7. We're going to need all these different bits for this example. Let's jump into our problem. So we want to add the binary number 1, 0, 1, 1, 0, 1, we want to take our binary number 1, 0, 1, 1, 0, 1 from 1, 0, 1, 0, 0. Okay, 0 from 1 leaves us with 1, 0 from 0 leaves us with 0, 1 minus 1, leave it with 0, 0 take away 1, leaves us with 1, 1 from 0 we cannot do, so we need to borrow. This becomes 0, this becomes 2, this will then become 1, and we can bring down our 0. So this is the number we've got. So we need to check to see is this correct. So one thing we can do is, you probably don't know what this binary number is in decimal. So it's always good practice to check our answers by converting our binary numbers to decimal and then taking them away and seeing if we're correct. So for this example, we can start off with 1, 0, 1, 1, 0, 1, and we can add these together. 32 plus 8 is 40, plus 4 is 44, plus 1 is 45. So I wrote down my next binary number, which is 10100. So that's equal to 16 plus 4. So 16 plus 4 is equal to 20. So we all know if we take 20 from 45, it will leave us with 25. Our next question is this binary number 25? So I wrote down my binary number under my grid, and it's equal to 16 plus 8 plus 1. So 16 plus 8 is 24, plus 1 is 25. So our answer is correct. Okay, we're going to move on to our next example. This is our last example, and it's the most difficult one so far. So the first number that we want to take away from will be 1, 1, 0, 0, 1, 0, 1, 1. And the number we want to take away from this number will be 1, 0, 1, 0, 1, 1, 0. So let's start off. 0 from 1 leaves with 1. 2 1s will cancel themselves out, so it leaves with 0. 1 from 0 we cannot do, so we need to borrow. This becomes 0, this becomes 2. This will now become 1. The 2 zeros, 0. This here, again, we need to borrow. We can't borrow from this 0, so we need to borrow from this guy. This guy now becomes 0, this becomes 2. We need to borrow from this 2, so this 2 gets changed to a 1, and now this becomes 2. 1 from 2 leaves with 1. 0 from 1 leaves with 1. Again, we have our problem now here that we cannot take 1 from 0, so we need to borrow again. This now becomes 0, this now becomes 2. 1 from 2 leaves with 1, and we can bring down our 0. So we think we've got the right answer, but it's always good to double check it. So we want to convert these numbers into their decimal format so we know for sure. So let's start off with this number. So I've brought my two binary numbers. Over here, and we can see that our first binary number is equal to 128 plus 64 plus 8 plus 2 plus 1, which gives us a total of 203. So we can put 203 for this number. Now for our next number, it's going to be 64 plus 16 plus 4 plus 2. This gives us a total of 86. So we can put 86 over here. So if we want to take these two numbers away, it would leave us with an answer of 117. So this number down here must equal 117. So let's check it. So we've brought our binary number over, and we know it's equal to 64 plus 32 plus 16 plus 4 plus 1. And if you put this into your calculator, you'll find that it's equal to 117. And 117 is our answer.